Okay, so good morning all. We want to discuss today uh, two popular examples. One example for NP-hard epsilon approximation algorithm. Another example is for NP-hard absolute approximation algorithm. Okay, so let's start it with the NP-hard epsilon approximation algorithm. Example is on. Okay, so you know what is traveling salesman problem, so we can think of a graph. Okay, so this is, let's say, a graph given. These are labeled. Let's say this is S, and this is 1, 2, 3, 4, 5, 6. Okay. So this is a graph. Here we have to find a Hamiltonian cycle. Okay. So means one Hamiltonian cycle we may find covering all the vertices. Let's say starting with source vertex S. Okay. 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 So this is Hamiltonian cycle, and arbitrary Hamiltonian cycle. The graph G is containing a Hamiltonian cycle. Okay. And it's next we are interested to find the cost of travel. Okay, CT is the cost of the tool along a Hamiltonian cycle. So that tool, okay, um, TSP. So the problem is here, you know, determine the minimum cost minimum cost of 2, that is CT. Okay, so this is the problem. I hope you can understand it. Okay. So next, what we go for, we have a theorem, and we will see. We will today prove that we shall discuss NP hard TSP is NP hard problem and its epsilon. This is our point of discussion for today. Okay. So we have a theorem in this regard. The theorem is cycle problem reduces to e-Approximability reduces to epsilon approximation approximated approximation algorithm for TSP. This is our theorem, and we will prove this theorem. Uh, it is clearly convincing to us that yes, Hamiltonian cycle problem will be reducible to uh, I mean a TSP algorithm for TSP. But the case is whether we can find an epsilon approximation algorithm or not. Okay. So because if you want to find a TSP, that means you have to find a Hamiltonian cycle. Okay. So Hamiltonian. So okay. Here proof is straightforward. So let G equal to V comma E B a graph be in graph, okay, and N equal to cardinality of, okay. So and to there in graph G we are interested to find a Hamiltonian cycle and thereby want to produce a minimum cost 2. Okay. So for that purpose, so let's construct complete graph dash from G comma E dash from G following occurs, that is E dash is equal to the set of all those edge UV such that V belongs to V and age v comma v, u and v are not equal. Okay, so we can construct a complete graph. Okay, so what we are doing here, so we shall show complete graph g dash. So g dash, there exists no polytime algorithm polytime approximation algorithm to determine Hamiltonian cycle and or to determine minimum equals to, hence determine Hamiltonian cycle which polytime approximation algorithm run on G and G. Okay, so we take up an example. Okay, so we want to make it a complete graph. So okay, so this is the complete graph. So what we do here, so let's try to analyze. So what is the meaning of having, so hmm, oh, the other thing we must mention, such that here another model, here we define an a-Cost function is function on g dash, that is equal to 1 if comes to else it is some constant value k, otherwise. Okay. Now what we want here, uh, we want to investigate if it is possible to assign such a value of k. Okay, so if g has if g has a Hamiltonian cycle, and let's say hc Hamiltonian cycle, then g dash have corresponding to corresponding to is the corresponding Hamiltonian cycle with the cost equal to n. Okay, so if this G is containing a Hamiltonian cycle, can you find the cycle here? 1, 3. So you can find the Hamiltonian cycle here. So this is 1, 3, 5, 2. Okay, so this is one Hamiltonian cycle. We can find out the graph G is containing a Hamiltonian cycle. Right. Okay, so okay, let me write all these values. This is 1, this is the age cost is 1, this age cost is 1, this is 1, this is 1, this is 1, this is also 1, and other ages are new ages. This is k, this is k, this is k, this is k. The 4 ages were new, so their age costs are k. Now, what is the value of k we can have? Okay, that's we are investing. So if G has a Hamiltonian cycle, then that means all the vertices are covered, all the edges are covered. So okay, so in that case, so starting from 1, 3, 4, 5, and 2, and then finally 1. So total, number of edges will be n minus 1, and while covering 2 to 1, we will have total n number of edges, and their edge costs are 1. So sum up, after summation, we get the answer n. Okay, so this is the result. So if I can, if I travel around a tour and have the result, what is the result? If the result is n, I can immediately understand that G is containing a Hamiltonian cycle. Okay, and that will be the minimum cost too. Okay, now case is if G dash is does not contain, then okay, so then at least one edge of V is absent in G, introduced so in that case, okay, in that case, the cost of the tour, let's say this is C of t. In that case, you know, the cost of the tour will be at least one edge is missing. So the n minus 1 number of edges are there to complete the tour. So n minus 1 into 1 plus at least one edge which is introduced in G dash, that edge cost is k. So k plus n minus 1. Okay. So this is the cost of the tour. And this is not equal to, this is greater than equal to. If we have more than one edges which are introduced in G dash, so this will be n minus 2 plus 2k. So this is greater than equal to, in the next line I am writing k plus n minus 1. Okay, so this is very important. We have come up to k plus n minus 1. We will be using this method. Now, the case is, now if the value of k we can assign here, we assume okay, that k is greater than 1. Okay, so uh, so the algorithm A can output, that is the solution to SP on G dash. Okay, whereas that is the approximated solution k plus n minus 1, whereas the exact solution n if G has uh, HC. So if G is containing a Hamiltonian cycle, output should be n. But the approximation algorithm can generate an answer k plus n minus 1. Okay. So in that case, we want to investigate whether that algorithm is epsilon approximation algorithm or not. So from the definition of epsilon approximation algorithm that uh, you know that the ratio of f star minus f bar by f star absolute value must be less than or equal to epsilon for some epsilon. Okay, we have what we have f star I is your n, f bar I is your k plus n minus 1. So we have here n minus n plus k minus 1. It is less than or equal to epsilon. Okay, so in the next step we have uh, 1 minus k by n less than equal to epsilon, and as k is greater than 1 we can remove the absolute sign, absolute function, so absolute bracket we can write there that k minus 1 by n less than equal to epsilon, k minus 1 by n less than equal to epsilon. Okay, next line we have is less than equal to 1 plus epsilon n. So this is a very important deduction we have made. K is less than equal to 1 plus epsilon for some positive constraint. So if this is satisfied, then we can this is the required value of k, which can be assigned as h cost, positive h cost. Okay. Okay. Next, what we do, we choose k equal to 1 plus epsilon. Okay. So from this we choose this. And, we shall have a break because it will take 1:30. Okay, I mean 1 hour 30. So after completion of this example, so we choose k plus k equal to 1 plus epsilon. Now what we shall have if if again we reinvestigate if G contains then Ct will be greater than equal to n plus k minus 1. So n plus k minus 1, right? 1 plus epsilon n minus 1. Okay, because here, okay, from we give this number, this is 1, this is 1, let's say this is 2, okay, so it has 1. Okay, so we put the value of k into that 1, so we will get ct greater than equal to n plus 1 minus 1. Next line we have that is equal to 1 1 get cancelled, so n plus epsilon n, that is 1 plus epsilon, whereas if G contains HC, the cost to has to be n, and we are getting Ct greater than equal to 1 plus epsilon n. This is the approximated answer. Okay, so Ct is the approximated answer. So in that case, so now the difference, absolute difference between f star I and f minus I. So f star I is f bar I. So absolute value of n minus in bracket uh, 1 plus epsilon n. Okay, so this value, n, 1 plus n epsilon n, sorry, epsilon into n. Okay, so this value, second term, n minus 1 plus epsilon n, the second term is, can be increased. This is the minimum value according to Ct. Ct is greater than equal to 1 plus epsilon n. That means here we are putting the value of Ct, and Ct is 1 plus epsilon into n or more than that. So that means overall this expression becomes this or less than this. So this is not equal to, this is less than equal to n plus n minus 1 plus epsilon into n. So in the next line we can write that this is equal to absolute value of this is n minus n minus epsilon কেটে গেল, কি হচ্ছে মডুলাস অফ epsilon epsilon. Okay, so in the next line what you can say that one plus, okay, before that we will want to prove this theorem. Hamiltonian cycle problem reduces to epsilon approximation algorithm for TSP, right? So, and we have already proved this, so I just missed the point to show you. Okay, let me do it later. Okay, so here what we have the model. So we have proved that the model of epsilon approximation for TSP as follows. This is important. That is okay. So the out Ct A, it will produce the result as the minimum cost of the two. So Ct is equal to n contains and it is greater than equal to, okay, greater than equal to 1 plus epsilon n into n if not contain Hamiltonian cycle. So this is the model, and okay. So if Ct equal to n, we can understand G contains Hamiltonian cycle if that is good, not greater than, if that is greater than equal to 1 plus epsilon into n, so it is not having any Hamiltonian cycle. And in this case we have assumed that we have taken the value that k is equal to uh, 1 plus epsilon into n, 1 plus epsilon n, 1 plus epsilon n, right? Okay, and this is the theorem. So Hamiltonian cycle problem reduces to epsilon approximation algorithm. Okay. Now, using this theorem, we further investigate. What we further investigate? See. So after this, what we have, we are taking that. Um, So at this moment, the Ct is the approximated answer 1 plus epsilon n. Okay, and let's say n is the exact answer. So in that case, what we have, this is epsilon n, means uh, the fractional value f star minus f bar I. There is f star I and this is less than equal to epsilon n. Epsilon. Okay, so the numerator is epsilon n, this is n, so epsilon. So this is very fine that we can have an algorithm which is epsilon approximation algorithm to determine whether G is Hamiltonian cycle or not. Okay. So next, but this is not yet done, because if we further investigate, we will come up to a very important result that we want to show you. So this calculations are not in the book Sahani, so please try to understand in the lecture. Okay. So what we have, if we have case 1, and that is okay, greater than equal to, we have seen that k is equal to, k come up to 1 plus greater than equal to 1 plus epsilon n. So epsilon. So if k is chosen to be greater than equal to 1 plus epsilon into n, then what happens actually? Okay, so we may have two sub cases. In one case where the output Ct will be n or Ct will be 1 plus epsilon. We know that Ct can be n or greater than equal to 1 plus epsilon, right? So to determine whether G contains Hamiltonian cycle or not. So uh, in case 1, let's say k greater than equal to 1 plus epsilon n, and then we consider a sub case where the approximated answer C T is. So there we see a little bit derivation, that is, according to, from equation 1 we know that Ct is greater than equal to k plus n minus 1, right? That is equal to n minus 1 plus k. So n minus 1 plus k, and k is chosen to be greater than equal to 1 plus n minus 1. So 1 plus epsilon, if this value is larger more 1 plus epsilon n or more than this, then this will be greater than equal to. Okay, and we have n minus 1. This is um, 2 plus epsilon into n minus 1. So 2 plus epsilon. Okay, so that we assume the difference between the exact value and the approximate value. We know that the exact value is n, but the approximate value is 2 plus epsilon into n minus 1. So assume that difference is denoted by some delta. So delta equal to exact difference of exact comma approximated solution. Okay, approximate solution. So in the next line we have delta equal to let's say minus 2 plus epsilon plus epsilon n minus 1, that becomes plus 1. And we have this is uh, 1 plus epsilon 1 plus epsilon to n uh, so okay, it is plus 1, this is minus. Okay, so 1 plus n minus 1. Okay, okay, so what can we say about here? So this is n into some value 1 plus epsilon, and as epsilon is positive, so this is more than 1. So this is this value term 1 plus epsilon n is more than n. Some value more than n minus 1. So eventually this is, we can say that this is less than n if less than epsilon. For example, epsilon is very close to 0.99. So in that case 1.99 into n, okay, minus 1. So n is suppose 20 vertices. So we have 20 vertices. So this is 1 plus epsilon means 1.99 into 20 into 20 20, okay, and minus 1. Okay, uh, oh sorry, this is minus 1. Okay, you can't see. Sorry. So here you can't say anything. 1 plus epsilon. This is is a okay. So at this moment we can't come up to any conclusion. Okay, the difference is okay. So we leave it here. No issue. Okay. because in sub case 2 it will be clear what I am trying to show you. That is sub case 2. You know, greater than equal to 1 plus epsilon. In that case, again, from 1 we have Ct to plus n minus 1. Okay, so that again it is, you know, same case. Ct is greater than equal to 2 plus epsilon n minus 1. So here we have repeating same as the earlier one. Ct greater than equal to so that for epsilon. So this expression is irrelevant of epsilon. So you come up to that difference is this. So okay. So you know what we come up to, the result is, if the approximated output is, if the exact answer is Ct greater than equal to 1 plus epsilon n, that means the G is not continuing in a Hamiltonian cycle. But our approximation is Ct greater than equal to 2 plus epsilon n minus 1. And from there we come up to difference less than n. So if the minimum cos2 is approximated as less than n, so how can we have that result that G is not containing any Hamiltonian cycle? If G is containing any Hamiltonian cycle, the minimum cost should be n. But here we are coming that it is less than n, and that is not possible. Okay, so this is not possible. Okay, and also we just tally with this answer that Ct has to be greater than equal to 1 plus epsilon n, and that is you know, for any epsilon greater than 0, this is more than n. Okay, also okay, so not possible. It is violating, contradicting the theorem. Not possible as it's theorem. Okay, so we have found a subcase. Okay, though we are not able to find any conclusive result from this subcase, but in second subcase we have come up to a point, even if from the theorem we use a suitable value of k greater than equal to 1 plus epsilon n, and we have found a subcase if Ct is greater than equal to 1 plus n, that is violating the theorem. Okay, that means the algorithm A is not a generalized epsilon approximation algorithm possible. Okay, so this is one reason. Similarly, if we do similar analysis. So please try to understand the analysis what we have done here. It is not available in the book of Sahani. Okay, so strictly follow the lecture, and if you can't understand, just ask me, because what I am showing writing here now, it will be in the quiz. So if we do similar analysis, uh, case 2, and that is less than or equal to 1 plus epsilon, then you can show that case that violates the theorem. So hence show that there exists no polytime epsilon approximation algorithm for TSP problem. Okay, polytime approximation algorithm for TSP. Okay. So this is very important thing, analytical, very analytical. So this much analysis is not done in the book. So please try to understand them. Okay. So if you have any question, you can ask me, or we can have a break of 2 to 5 minutes.